Okay, another live video. I know, it's crazy. Let's see if anybody is in the stream. I have no person. Alright, let's see. So, today, my goal is to finish designing Groundbreaker on this live stream. I don't know if that's going to happen or not, but it would sure be nice if it did, because I've set some very ambitious goals for myself this week, and this is one of them, finishing the design, as well as finishing building a couple of model rocket kits I have, which is kind of why the basement smells like paint. You can see this one kit is kind of drying there. So anyway, yes, I've kind of made myself very busy with all of these little. That's a little project, but Groundbreaker is not. It's 15 feet tall. So anyway, what are we going to do now? We are going to go into OpenRocket and start designing. So I want to do a quick test and see if my mic mutes or not, because for some reason yesterday I was having issues with that. So I want to test that out real quick and see if that works. Okay, awesome. I figured out how to mute it. It was kind of weird because in OBS Studio, there's a slider where you can slide down. Okay, awesome. I figured out. There's a way you can slide the volume down for all the different mics there are, and I did that and it didn't work. So I tried something else. A tutorial I watched where you have to like go into OBS settings and change a bunch of stuff, and that appeared to have worked. So great. I figured that out. And now we are going to get going into we're going to go into OpenRocket and try to figure out how to finish this thing once and for all. So there are a couple of, I would say, like dilemmas or something that I need to make decisions on. A couple of them being like, alright, what type of system should I use to retain the motor, or the motors in the rocket? So, I have two options to choose from. One is the retainer, which I like it because it's the most, I would say, reliable, because it's a screw-on retainer that holds the motor in, and it's probably the most stable. So the pro about that is I'm guaranteed the motor's going to stay in there, and two, it's just that's really the only pro. But anyway, the con to the retainer is it takes up a lot of space, and so I'd have to make the rocket much wider to accommodate for that space issue, and so that kind of messes up the whole design thing, because then I have to design around the thing being able to hold the retainer, which is kind of what version 3 that I designed yesterday. That is why it ended up looking something like this, because I was trying to accommodate for that retainer issue. So you can see right here, I made the bottom really wide here, and this was trying to accommodate for that retainer issue because retainers take up so much space. So, what am I going to do now? Well, so my other option is I can use what is called a friction fit. And so what a friction fit is basically it is another method of retaining a motor, and there are so many different methods. But anyway, a friction fit is basically you take a motor, and let me see if I can demonstrate. I have a motor on my desk here, so what you do is you take your motor, and what you do is you take masking tape and you wrap the masking tape around the motor. Okay, so pretend I have masking tape, you wrap it around the motor, and then you put it in the rocket, like so, and the motor is held in by friction. And then, on top of that, what I would do is I would take more masking tape, and you can see the little bit of the motor that's sticking out right here. I would tape it really well around the motor and the tube that it's in, and I would tape that really well, and that would hold it in. However, so that method would solve the issue of having to make the rocket much wider to fit the retainer in, but I guess the con or the unknown about friction fit combined with a tube tape is that I'm a little skeptical about it because I feel like it's risky, you know. And the thing is, with the ejection charge having about 45 pounds of force, a little more than that, to shoot the nose cone off, or to the top of the rocket. But anyway, 45 pounds of force is a lot of force, and with that amount of force, you need it to be in there really well. So I'm very skeptical on using tape, because while I have done some research and it does hold much more than you would think it would, I don't know, and I don't think it will be able to hold 45 pounds of force. So I might have to go with the retainer and try to design around that. The problem is, though, is I have to really change the design of the rocket. So it's a big decision to make. And then another thing is I need to look into, I would say, motors or something, because different types of motors. Because while I originally planned on using a G80, two G80s, the problem is I need to figure out like how to get the ejection charge to be the right time I want it to be, because like I said, with the current motor I'm using, there's only 3 commercial ejection charges you can buy: a 4-second, 7-second, or 10-second delay. And so I need to look into, because I don't know at the moment if you can drill out ejection charges on single-use motors. I have to look that up. I do know, I think on reloads you can actually, with those motors, there's a tool and you can drill out some of the black powder, and on the tool will tell you what time you're decreasing your ejection charge to. But the problem that is, I don't know if you can do that in single use, and I have to look into that tool. So that's some other research I need to do on this stream. So those are some of the biggies, and I'm trying to think what else. Really, I think it's just motor retention and then delay time, and those should solve my issues, but you never know. So, I guess let's get into that and see if we can figure some stuff out. We'll get this live stream going. Hopefully I can get this finished on this live stream, because I really want to get this rocket finished. So anyway, enough of my blabbing. Let us get to designing here. Alright, so if we pull up YouTube here, let's look at some motor retention systems. Okay.
In this video, we're going to talk about engine mount retention. That means holding the engine inside the rocket kit securely so that the engine can't either slide forward or slide backwards. Because if the engine were to slide forward, it would push the parachute out prematurely, and if it slides backwards, according to Newton's laws of motion, for every action you have a reaction. So if this comes out this way, the rocket's going to go that way without pushing the parachute out. So we want to make sure that the engine stays in its place. On some rocket kits, like this one here, the engine hook is kind of loose and it's really easy for the engine. It might pop out. For this, what I like to do is to take some thin tape. If you don't have thin tape, you can just go and get some masking tape and cutting it into strips. But I'll just take a piece of tape and just wrap it around the engine hook and go around the outside of the motor like that. And what this does is it prevents that engine hook from being able to pop upwards so that the engine would kick out. So that you can pretty much do this on pretty much every rocket kit that has an engine hook, and it's always a good thing and it's never a bad thing. So that's my first recommendation there. We get a lot of calls from customers here that have rocket kits that use the Estes E engine, and then they wanted to decide, they want to fly with a D engine, but when they put it in, it goes way too far forward. So what they need is a spacer, and they always say, well, where am I going to get this spacer? Well, if you've flown a D engine before, you probably have an empty case, and you can make a spacer out of that case. Just take it and just cut off, and it's exactly 1 inch. So you just measure 1 inch, take your saw blade, and just cut 1 inch. And you get your spacer. You put your spacer in first,
now, so this is kind of,
and then you slide your rocket engine in, and it holds it in place. And there you go. When we get to 29 millimeter diameter kits, you'll find very few rockets have engine hooks. And it's because of this problem where the engine wants to kick out. So again, always wrap tape around the hook, especially on the 29 millimeter motors. The Aerotech kits are the only ones that I know that have the engine hooks in them. And they were designed for the RMS 2940 to 120 casing, so that when you slide the casing in, it will hook over the end of the nozzle end. But when you're using other engines in it, like single-use motors, here's an F engine that would fly nicely on this kit. This one doesn't have, since it's shorter, it's going to slide too far in. Let me see, like that. So what we need to do is to put a thrust ring in there. Aerotech gives you these little rings that typically you glue on the back end of the engine like this, so that when it goes into a rocket, it butts up against it like that. And what you'll typically do on most kits is that don't have engine hooks, is just take your masking tape and you'll just wrap tape around the outside like this. Now, many people are afraid of this, wrapping tape around the outside. But actually, this works really good. That engine is not going anywhere, either forward or back. So this is typically how we do 29 millimeter motors.
Now, what engine was that?
Wrapping tape around the outside.
That was like an F engine or something.
And you'll just wrap tape. You glue on the back end up against it like that. This, so that when it goes into a...
I need to see what engine that is.
Glue on the back end of the engine like this.
Oh my
gosh. When it goes into a rocket, slide too far in. Let me see like that. So what we need to do is to put a thrust ring in there. Aerotech gives you these little rings that typically you glue on the back end of the engine like this, so that when it goes into a rocket, it butts up against it like that. And what you'll typically do on most kits is that don't have engine hooks.
So this is what I'm scared of, because, like, I know he said it works, but that was on an F engine. I'm using a G80, which is, like, gosh, a lot more powerful than an F engine. So, and I'm using 2 of those, so that's way more power. So I'm really scared to, I guess, design the rocket so that it works with this tape method, and then realize it doesn't work, and I have to rebuild the rocket and redesign it to work with retainers or something. So this is kind of what I'm scared of, because I don't want that to happen, but at the same time, I don't want to design a crappy rocket just so it fits retainers. So I'm really stuck here on what to do.
Just take your masking tape and you'll just wrap tape around the outside like this. Now many people are afraid of this, wrapping tape around the outside, but actually this works really good. That engine is not going anywhere, either forward or back. So this is typically how we do 29mm motors. But on the Aerotech kit, because it would go too far in, you got to move that ring further forward on the nozzle end.
With 29mm motors, so maybe it will
see
work.
This one here, I put it probably about an inch forward so that when it slides in,
if I go down that road, it's not going to work.
That hook will latch over the side. And then I would wrap tape around that engine hook so that it won't pop out at ejection. Okay. One of the reasons why we don't put engine blocks in these is because of the different lengths of the motors. And let me explain with this one here. So now this was an F engine. Now to say I decided I wanted to fly with a G engine. Now the G engine is a lot longer than an F engine. See, here's an F engine and here's the G engine. Now if I put that G engine, and this one does have an engine block in it, what happens is now the engine doesn't go in all the way. And you're basically stuck. You can't really do anything in this situation. You don't want to let the engine hang out this far because it throws the center of gravity too far backwards and it could make the rocket unstable.
Okay, so I get that part. I kind of wish that kit didn't have an engine block in it, just so that he could put it in there and say, okay, this G engine, also will be fine being taped in here, and then that would have been the final okay for me, saying that taping it would actually work. Because with an F engine, those things are still pretty powerful, but I still don't know if that's going to work with the G. And so I'm very skeptical about masking taping an engine into a rocket. Yeah, because the engine, one of those G80s, I think has 24-ish pounds of thrust. So that's a lot of thrust, and I don't know if that will work very well.
So typically, what I tell people is you have to design the rocket to take the longest engine possible. And I recommend that you just leave the engine block out altogether. See, these new engines, and the reloads are the same way, they have the engine block built on the back end of the rocket. And if it doesn't have an engine block on it, just take some tape and you can build one up. Or you can take the ring that Aerotech gives you to build one up. And just keep wrapping it around until you get a nice thickness there. And it'll take probably about 7 or 8 wraps of tape to build up enough thickness so that when you slide it in, then you can wrap tape around it so that the thickness of the tape equals the thickness of the tube, so that when it goes in, it butts up against there. That means it can't go further forward. One of the newer things in rocketry is called engine retainers. And these are a 2-piece aluminum assembly.
They are heavy duty
where one
aluminum, but the
end
problem is they
is
take up
glued
more
onto the
space
rocket
than I
like
have
that.
available with the current design.
Then when you slide your rocket engine in, it will butt up against that, like this. And then to keep it from going backwards, now this part here is glued on, and you're going to use epoxy. And then this other part is just screwed on, and that's what keeps it from sliding backwards. Now these are pretty nice, and they really make the rocket look like it was designed and built like by a professional. So I do recommend these. They are a bit more expensive.
They are very expensive.
But it gives your rocket that nice finished look that you might not otherwise get.
One of those is like
now
$40.
Finally, if you have a rocket, let me see, take this one here. Now this rocket was built according to the kit instructions. And the instructions said put the ring, this aft centering ring, on the back end of the rocket and then glue the engine mount up to it. Now when you do that, the engine block will prevent it from going forward, but now I don't have anything I can wrap tape around to hold it from going backwards. And there's really not enough room here to glue this engine mount retainer, this part that gets glued on. So in this situation, we're basically stuck. The only thing that we can do is to do a friction fit. And I don't really like friction fitting, and this is the method of last resort. But if you are going to do friction fitting, put the tape towards the nozzle end, so that it's easier to get the rocket in and out.
So that video was semi-helpful. I don't know. I'm still pretty skeptical about taping. I need to look that up. Oh yeah, Google. Alright. I'm kind of like figuring this out as I go, so honestly, I don't know. This is what an older version of a G80 looks like. The one that I'm using. This is a much older version, but gosh, when was this made? This has got to be old. I was lucky. Guy didn't need it anymore, and I was like, I think it would work on a scratch building. Yeah, 1990s. Old one. I don't know. So let's see. Take this rings. Let's see if he has an article on it. He has a video, but let's see if his article is better. Apogee Peak of Flight newsletter, motor retention techniques for minimum diameter rockets. Couple of drawbacks to friction fitting. The first is that you never really know if you have enough tape on the rocket to hold it securely. Too many times it isn't enough. When you hear it, what you hear is a loud pop, and then the rocket comes crashing into the ground with a full head of steam. That wasn't enough, but too much tape can be a big problem too. The motor case might be difficult to remove after the flight. I've personally ruined a rocket of rockets by trying to get a stuck engine out. Here's what happens that causes the motor to get stuck. After the motor is done burning, the case starts to get hot. It takes a while for it to get hot as the heat has to propagate from the inside to the outside. But as it heats up, it may start transparent. It may start to expand. This makes it tighter in the tube than when you start it. The first way to solve the problem is to design and build the rocket so the fins are shifted a little bit forward. This leaves a straight section behind the tube where you can wrap tape around the engine to hold the motor in place. See illustration on the next page. Again, I've been asked, does a layer of tape wrapped around the motor really hold it in place? Yes, it works fine. One thing that I'd like to do is put a layer of glossy, transparent tape on the back end of the tube. This does two things. First, it protects the paper tube from fraying, especially if you have bare tubes because you didn't paint them. So when you pull the tape off and remove the spin motor, you don't remove the top layer of paper tube. Second, when the adhesive on the masking tape holding the motor in the tube gets hot, it gets gooey, so when you remove the tape, goo is left on the tube. By having the glossy tape underneath, it's easy to clean off the goo residue. Alright. What is this? Oh. What is this? Okay. So, what this is showing, so maybe I could get away with doing this tape method. It is on the risky side, but it's not impossible. So, is this Kevlar cord in this diagram here? It probably is, I doubt. Yeah, it's Kevlar. So, what is this saying? So basically, what I could do is I could do the friction fit above, combine that with this and this method. So all three of these methods. So I could tape it around the tube. Obviously, the 15-foot rocket, it's not a minimum diameter rocket, but it is, I could tape the motor around the inner tube that it'll be in, I guess, if that makes sense. So I think this concept should apply to what I'm doing to some degree. And then the other thing is I could, do that tape method there, then also combine it with the lariat loop method. And what this looks like is basically what you do is you tie a slip knot here, and this is essentially how you can attach your shock cord to the rocket. Now, let's see. A hole for shock cord. Let me actually read this, because I don't think this is for your actual parachute. I think this is just to hold the motor in. competition modelers swear by this technique. An added benefit of the method is that it leaves the inside of the body tube free of any bumps or bulges like the Estes-style shock cord anchor. Okay, so this helps the recovery device slip out the tube cleanly. This is important when you are trying to stuff a big parachute. A small diameter of 100-pound test explosive while showing. And the following two figures illustrate its use. Note, use of a lariat loop assumes that the engine protrudes from the model at least 1/4 of an inch when installed for flight. Okay, so I'm going to bookmark this under model rockets. In line with one of the model's fins, a small hole is drilled through the body tube wall. Pass one end of a 30-inch or longer Kevlar cord through the hole and out the tail end of the model. Okay, Kevlar through the hole and out the tail end of the model. Okay, now slip the lariat loop around the normally exposed end of the motor casing and cinch the loop down tight. Enough tape should now be added to the motor's exterior to allow for a smooth fit of the motor into the model. Remember, pull out the slack that will form in the Kevlar line as you push in the motor. Okay. Oh, okay. I get it. So this, I'm not sure though why that is. I don't know why they're showing this Kevlar cord coming out of the rocket tube, but I think what this is saying is that instead of your typical Estes shock cord mount, such as this right here, this shock cord mount, essentially, it's a piece of paper. Let me see if I can get a flashlight on this. So inside this rocket, this is going to be hard to see. So yeah, there you can see. So see in there you can see the shock cord is glued into this piece of paper, which is then glued into the body tube, and that's how the shock cord stays in the rocket. So it's saying instead of using, and this is a typical Estes kit, it's saying instead of using the typical Estes kit method, what you can instead do to secure your shock cord is use that lariat loop method. And so what that does is you're basically tying the shock cord around the actual motor itself, and that is what the shock cord is mounted to. So when your parachute is ejected, instead of the shock cord kind of being its own separate entity like the Estes kits, it's basically as the rocket is, parachuting down. Like pretend there's a like let's say the nose cone's here, right? Your parachute comes out, and then as the rocket is parachuting down, it's kind of essentially, as it's parachuting down, it's tying that lariat loop even tighter because it's a slip knot. So it essentially tightens itself as the parachute comes out and the rocket's descending. So that actually is a really good method. And I might see if I can combine like all three of those methods and just use that to retain my motor and to mount my shock cord. Now, of course, I'm not, I guess, completely confident in this design, but it actually is a pretty smart and unique way to do things. So, I put my rocket back up on the vise, and now we can continue to talk about Groundbreaker. So, I might combine all three of those methods Now let's like look into some stuff about retainers. So, so I bookmarked that. Let's see if there's any other interesting things. Engine hooks, as he said, are good, but I couldn't like find any 29mm ones like he was showing in the video. And that's it. So, what are retention apogee ones? All right, let's see if this is the same article. Okay, so I don't know. It does seem as if this taping method is a reliable way to retain motors. I'm still a little skeptical about it. This is something I would definitely need to do ground testing on. So I don't know. Let me see here. So let's look up retainers, and let's see if I get anything that pertains to what I actually looked up. There we go. 29mm retainer. We are looking at. This is the super cheap Estes version. Okay, so this is another way to hold your engine in, and it is reliable by like screwing the engine in, and this does work. But since the material I'm using, I don't think would be suited for driving through, screws through. So anyway, let me just click on 9mm retainers. All right, let's look up that, and then we will figure out the delay. Okay. This is just another form of those screwing retainer things. Alright, so it's 29mm. This is the Estes one. This is the bulkiest one, though, so 29mm retainer out. These are ridiculous. An outer. Fits 29mm tubes with an outer diameter of 1.21 inches. Okay, so let's see if we can do some math here and figure out actually what this is, how much space I need between them. Alright, so cap diameter, height. Alright, so you're looking at cap diameter for, what is this? This was the RA 29mm, just plain L, not L2, L3, or P, or whatever. So let's see, cap. So that's, so they all have the same outer diameter of 1.575. So the cap diameter, as it says in this image, is that measurement. So this is the measurement we need to know on if this would fit in the rocket. So if we take a calculator, and since we're doing two G80s, we double 1.575. What we get is 3.15 inches. So maybe I wouldn't actually well, no, I would. So this actually isn't as bad as I thought. So I might stick with the retainer, but I'm definitely going to have to go into this design and see how that affects it. So the inner diameter currently of this tube is 2.75 inches. So I'd have to up that a little more, probably up to like 3.25, I would say. And that would bump my outer diameter up to 3.5 inches. So I don't know how this is honestly going to affect my design here. So let me see what happens when I type in that stuff. Alright, so 3.25. Whoa, okay. Yeah. I do not like that. We are having some issues. So let's fix this transition. Half diameter is now 3.5. And the shoulder is also 3.5 now. Alright, aft shoulder is 3.5. No, it's 3.25. .25. That's what is another 1 point? Of 2. I'm thinking what that means is that you're separating all of the tubes by 1 tube diameter. So let me see. Right now, I think our outer diameter of this tube, it's in millimeters, is 30.5. So 2 would be like 61. So what math is that? 61. No, it's 30.5, and then it's divided by something. So what we need to figure out is how far apart these things need to be spaced so that I can get 3 retainers on it. So a retainer's diameter is, what did it say? It was 1.575 inches. So what is the actual thickness of that? Because that's all I need to know. So what I need to know now, or what I need to figure out now, is what is the thickness of this thing from here to here. So what's the actual thickness of both of these things when it's screwed on? That's what I need to figure out how far apart these engines need to be. So length or thickness is 0.5. Wait. So I just have an inner diameter and then I have length or thickness. Okay. What can I do to figure this out? I don't know. Let's see what the actual thickness is. Alright. I suppose, since I don't actually have that, I have a retainer in the back, but it's not the same one picture. Let me see if I can just measure the thickness of that. Okay, so I got about 1/4 of an inch. So I need to figure out how to separate these by about 1/4. So what is... That's 1.2 inches. And then I just need to figure out how many diameters to increase that so that it's a distance of 0.25 apart from each other. And that would effectively solve my issue. Right? Let's see. Let me see here. I'm wondering if I just clicked. Wonder if I did that instead. Let's see. Cluster. Show right. There's. I'm getting distracted. Okay. This component is a motor mount. Motor overhang is definitely going to be something there. So let's say an inch from the rocket. 2 inches. Oh wait, is that going up in the rocket? Hold on. Because then I need it negative. Nope. I'm good. I'm not sure. There we go. Yeah, I don't know here what I'm gonna do. I gotta think about this. But I definitely do not need an overhang of 2 inches. I'll just say 1.5. Where was that? Okay. So 1,015 feet. I don't hate that. I don't hate my stability cal. Let me check that one more time. Running that. Edit simulation. Let me up it to like 20. If I get an error with this, I'm not going to be happy. Yeah, I'm not happy. It should be able to handle 20, at least. That should be the bare minimum for over designing this for safety. So I don't like that because it, you know, that's not kind of what I want. Okay, so it doesn't like increasing the root chord. It does not really care about the tip chord. Let's see. It really cares about the height, though. wider or whatever, the bigger I make these fins, the better. However, I don't like that. What was my angle on that, though? 'Cause the problem is, I'm kind of trying to figure out a way to get this angle to be an exact number-ish, so that I don't have to... Alright, so you can see that it's a little happier now. Gotta increase that stability cal. Let me up it and push it more. Still happy. Alright, that's what I want. That is definitely not gonna work, but that is okay. Mostly good. Okay, so this is good. This is good. So I've increased the altitude, but now I still need to figure out retainer and retention. And I am still stuck on those things because, yeah. So, what are my options? What altitude is my parachute going to come out? Because that is also something I need to do, because sometimes higher altitude is not always better. So, let me see. Let me down that to my average wind speed of what is probably going to be 15 on that simulation. I'm getting like 996, which is insane. Let's see. Velocity at deployment is good. I don't like this off-rod velocity. How do I improve? Oh, I know. Because the launch rod length is not set to what I actually have it in real life. So this is a... Oh, neither is this one. Yeah. That's interesting. Nope, this one is. This one isn't. Okay, that was at 72. Okay, so hopefully they should fix the problem. Oh, thank God. 70. That's a very long launch rod still, though. Alright. Okay, that is much better. Apogee is a little bit better now as well. Okay, so I don't hate this data, but I still need to fix some things. Let's look at fixing this dude. Let's do an 8-engine cluster. Oh my God. Oh, that is so stupid. I kind of want to do that. That is kind of cool, though. 2,300 feet. Oh my God, that is absolutely nuts. Yeah, no, I would never launch that. That is the dumbest thing ever. Let's see. Radio position, override, cluster, tube separation. So, one tube is equal to 30.5. So let me see if I can figure this out. Let me get a piece of... Oh my God! I just killed my computer. Well, hold on 1 second. So one tube diameter, which is equal to 30.5, and then let's see. What am I looking for here? I want it to be separated by, how much did I say? It's a 1/4 of an inch of separation. So I want it to be 0.25. 5. So let's see if this will solve my issue. Let me think about this. This is probably the most boring live stream ever, but this is the designing process, so, and I'm also an idiot. Let's do like a 1 point. I'll do. Effectively put that separation where I want it. So, if I make this inner tube have an overhang, so let's see, a position relative to the bottom or the slash parent component, back view, side view, alright, inner tube, and I click this, -1, that will just effectively move this entire assembly. So why don't I click this overhang, cluster overhang appearance, where was it? I'm not even paying attention. So let's do 0 overhang, and it fits not perfectly. How long is this motor? It said it was 124 millimeters. So why doesn't it fit? G78s. Oh, that might be why. How long is a G78? Because that's a different motor. Alright. Let's duplicate this site. Holy moly. I forgot how expensive these are. Alright, it is 146 millimeters. So, I just up that to like 147-ish. Boom, it fits now. Okay. My altitude went down a couple feet, but who cares? And let's see here. Motor cluster radial. Motor cluster radial. It was this one. Boom. Let's call it a day. My life is so much better now. So how long exactly are those retainers so I can overhang it from the actual rocket? And let me check. I'll be right back. Roughly an inch, but let me see what the actual retainer I'm buying is. If I'm actually buying 3 of those, that is a ton of money. Alright. So, cap diameter, what was I looking for? Oh, I was looking for cap height. Cap height is 0.55 inches. So, 1 should be plenty. Let me see. So that design right here would work. Not this one. Right here. This should work with the retainer. Keyword is should. And then let's see. What else? Now there are still unknowns, right? Such as when my actual parachute deploys. And I really don't want to put 3 motors on this thing, because that is way more power than I like. So, plus, if we add to the cost, that is a ton of money more. So, 0.44 times 3, that is $112 on engines, plus what is this retainer? Cost 26 plus 26.84 times 3 is that. Yeah, that's about that's about a lot of money. That's $193-ish, just on some of the motor stuff. Which, I mean, I guess is not terrible. I don't want to be cheap with this, and I'm thinking that might be my best route to safety. But at the same time, I really am skeptical about using 3 motors. So let me see if I can cluster this to 2. I'm still at the right radial position, right? So I guess now it's really just that. I don't know. I might make a separate copy and mess around with just 2 motors at another time. This is something I might need to talk to somebody about. Let's see, and then what's my actual space here? And I also need to calculate fin tab stuff. So let's see if I can figure that out. I don't know. What are these purple things here? Inner tube. Is it an inner tube? Is that what that is? Oh, that is an inner tube. Alright, so let's fix that. Elevators for life. Alright. Let's see here. Ball thickness 3.18 meters, which in inches should be. Yep. Alright. Inner diameter is 1 point. No, that's not what that is. More because it's different. What is this diameter at this point? I don't know. Let us change our view. Back view. No. Like this. So it's 58.6. That looks like it fits. Our outer diameter, like this is 0.125, so it should be in inches. I'll flip that to that. That'll be 0.1. So let me increase this guy. inch matters. My famous quote. Alright, let's see. Bottom, how about, yep, bottom's good with me. Let's go all the way up here, up to like 59 inches. That's where it would be. That doesn't affect it. Alright, I'm just putting on there to see something for. Yep, so that's a bulkhead. It thinks it's plywood though, so I can probably tell it is plywood. And that is my first. That looks kind of cool, but also kind of terrifying. Yeah, dude, that is absolutely terrifying. I'm scared that I'm doing this so much. I am absolutely scared. I'll probably send the, yeah, I think that's what I'm going to do. I am absolutely scared so much right now, though. Well, we'll close out a photo studio and change this bulkhead. Oh, it is cardboard. I don't know why it looked like plywood to me. Is this also plywood? Nope, that's bad. I want plywood. And I need to figure out what kind of Bluetooth. I don't know what that is. Also, let's just do cardboard. Let's just leave it at cardboard. And then component finish. Let's change that up to, where is birch plywood. Plywood, birch, close. Now when I click on this again, it should say plywood, birch. Good. Simulation. This one. Wow, look at that delay. It's almost perfect. So yeah, I don't know. And then our speed is 0.24, Mach 0.24. So let's change that. 184 miles an hour. That is quite a bit compared to last, which was actually kind of like that, or that. So I went up from, I think it was 146 miles an hour. Yep, to 184. That's a pretty significant increase. So I don't know. There is definitely a lot of stuff I need to figure out still, and I will probably do this some more, see if I can figure out with just 2 motors, because 3 is a lot, and I'm scared. I don't really want to do 3. It's pushing it. So I don't know. But let's see. So, that is kind of a 3 motor setup. I am probably not going to do this on a live stream, trying to figure out the 2 motor setup, because this live stream has been going on for a very long time. I can definitely tell, because it is now 3:35 p.m. So, for those who have joined, thank you so much, and hopefully I can continue this later, and figure out what I want to do with this. This is taking me a really long time. But anyway, thanks for joining, and that is our rocket at the moment. I'm going to make a copy with the new design and see if I can get a 2 motor setup to work. And yeah, so anyway, thank you everybody for joining and watching me mess around with designing rockets. and hopefully you learned something. I'm probably going to end the stream now, so thank you for watching. I still have some things to figure out, but I'm going to try to get this to work with a retainer. And then, like I said, I want to try a 2-motor setup, see how that works, and up it to a 3 if I need to. But hopefully this works. So thank you, everybody, for joining, and I guess I'll keep you updated on what's going on and all that stuff. So thank you, and